So now the sheet is being passed around is the same that you will find. Before we start, do you have some questions from what Claudia uh, told taught you today? Something that is not clear? Today we should feel free to interrupt me anytime. Okay. Today we should look at some exercise about the seesaws. I don't know why it stopped sharing. Um, and you saw that if we are at low energy, we have essentially the standard model is an effective field theory, right? Please. Right. Mhm. Yes. N- So I would agree with you that yes, we can set limits on the Majoran couplings, exactly because it's a different spectral shape, no? So we can try to fit it, but I don't know how to reply experimentally. I mean, who is doing this? How good it is, these constraints. Yes. Yes, yes, and in principle, um, in the Myron, this contribution with the three, also with the Myron and the electrons, you get okay, you get predictions for the rate, which depend on the couplings, and you are asking me about the nuclear matrix elements. So in that case, it should follow more or less the standard. I mean, correct me if I'm wrong, but it should follow the standard one in the sense it's also long range interaction, and there is no involvement of the quarks. This is my expectation for the Myron. But for other processes, as you were told also today, you can have interference of several contributions. Sure. I can draw it, yes. So the normal neutrino Salvete is without this line. Yes. Mhm. No, they do correlative flip. In fact, this vertex here should be the thing where, if you think about VEVs, if this guy gets a VEV, it will give you a mass for them, for the neutrino. So this is a correlative flip always. Otherwise, you will get zero, as was argued a bit. I mean, this is why the rate is proportional, or m beta beta is proportional to masses. Because if the masses vanish, you cannot do the correlative flip, and so the diagram cannot be, I mean, it's zero. Thank you. Any other question? So then we can go on to the exercises, which today are a bit out of order, in the sense that we will start with 2.4 and then go to 2.1. And we're going to do these first two exercises together. And later we will try to group as we did the other day. So 2.4, the question, for some reason, share screen is failing me. So what you saw in the lectures was that if you are at low energies, you have this Feinberg operator, no? So 2 lepton doublets, 2 Higgs doublets, and if you go to electric symmetry breaking, the Higgs neutral parts gets a VEV. Here you select the neutrinos, and this is basically a Majorana-Mas term for the neutrinos, which looks something like this. So whatever new physics or old physics you put here, if you can write a diagram like this where the arrows go in opposite directions, either both in or both out, you are writing a Majorana-Mas term for neutrinos. This is why today when Claudia drew the for loop diagram, I mean, if you looked far away, all those loops and etc., they are just part of a blob. The point is that you get a diagram which is non-zero with neutrinos going in and out. This is a Majorana-Mas for the neutrino. And what I was trying to show here is that if you look at the standard model as an effective field theory, again, as Claudia said, you can start looking for operators which are non-normalizable. So not just dimension 4, but you can go up in dimension. This is when you are completely, let's say, agnostic or ignorant of what happens at high energies. What is the true theory of nature? Okay, at low energy, we just see the effects of the high energy integrated out, and you get something which is effectively a blob. So this diagram with 4 legs going in, and it still respects the standard model symmetries as you saw, but it's unknown what is there. If instead, okay, I'm trying to show this to you, but I guess it's the, have to restart the meeting. If instead you have a powerful enough collider or a magnifying glass, you can look inside this diagram. So if you can, like the W, you can produce these particles. If you know actually the right theory, you can look what is going on here. And this is what happens in the seesaws, is that these are considering tree-level exchange of some extra particles. So if you believe in your full theory that there is this guy, this right-handed neutrino, which doesn't transform under color, doesn't transform under isospin, and has no hypercharge, if you have this guy there, you can think of drawing the type 1 diagram that Claudia drew. So something like this, no? And if it's too heavy, the propagator will kind of give you the 4 fermion, sorry, the Weinberg operator, 2 fermions and 2 scalars. Seems that I'm back. So the first exercise is to understand why there are only 3 types of seesaw. This 2.4. And by this I mean, of course, Claudia's shown you so many diagrams that you think there seems to be a lot of these kind of ways to produce neutrino masses. But seesaw here implies the tree-level exchange of some particle. And there are only 3 types. So we should think together why there is no 4th type. Do you have some idea? In particular, I mean, you had type 1 and type 2 and type 3. Type 1 and 3 were very similar, right? Because there were fermions. Here the question is, can we have another diagram like this with scalars? So can I erase this part here? So this is type 1 seesaw. Type 2 seesaw, what kind of couplings did you have with the delta, which is a Higgs triplet? Do you remember? For type 1 and type 3, you had these couplings, right? So L with the Higgs and with the N. If it was type 3, instead of fermion here singlet, you would have a fermion triplet. What about in the type 2 seesaw? Okay, there was a vertex with 2 Higgs. And? Yes, right. There is this one. This is a new particle. Sorry? Does it couple to fermions? Yes, should couple to the leptons. No, we want to generate, at the end of the day, a mass for the neutrinos. My meeting is getting disconnected and reconnected. So I'm giving you a lot of chance to recall the lecture. You can go to your notes. Can you tell me what else does this delta triplet couple to? To which fermions? Which standard model fermions? Sorry? Please check your notes. You are free to do so. So the fields which contain the electrons, yes. Okay, so finally I have some slides. And here is the answer. No, I mean, this is the diagram of Claudia, but a bit rotated, because in quantum field theory, if you have one, you can use exchange symmetry and draw it in any orientation. It connects not just to the Higgses, this coupling here, mu, which is exactly the one we wrote here. But there is a coupling, Y, Yukawa coupling, but with leptons. So these are big L. Okay? In particular, something like this, so that there is no cancellation with the projectors. And there are indices in these couplings, right? Because you can couple, here it's not explicit, but you can couple this guy to any pairs of lepton doublets. Diagrammatically, this looks like that. So you have the doublets which are the neutrinos. There is this heavy field, and there are the Higgses. How do we get a mass for the neutrinos here? How do we make it look like that? So here we have the lepton doublets, right? These L's. You recall they are new L's and the charged leptons, no? But we are talking about neutrinos. What needs to happen to differentiate the two components of the doublet of SU2? Symmetry breaking. Electroweak symmetry breaking, where this Higgs gets a VEV, and the contractions will give you coupling from the neutral part to the neutrinos, and then your diagram looks something like this, nu L, nu L. This will be the VEV of the Higgs. And if this guy is very heavy, these are like numbers, no more external legs. This guy is very heavy, everything goes into a blob, and you get that. Okay. So there are these three-level exchange mechanisms that you exchange a heavy, where you exchange a heavy particle, and when these Higgses get a VEV, you collapse everything into a mass for the neutrinos, like the Weinberg operator. And now we are interested in answering, is this all? So what if we had a scalar, which is not delta, let me call it S. Let's discuss together, let's call it S, and try to find out why this diagram doesn't work. Delta is a triplet of SU2. Why can't we have a singlet of SU2 here? So there's no problem having these vertices with fermions and scalars, right? Because otherwise we could not have even that. It's not about the fermions or the scalars. If this guy doesn't transform under SU2, exactly. Exactly. So to repeat, we have to check the appropriate symmetry transformations. If S is a singlet of SU2, it means its isospin is 0, so it's just a field, okay, no longer a doublet. You need to contract these two doublets, and you can make this interaction here. It will be taking, so let me change these guys here. So instead of delta, we have S. Okay? And these guys will be doublets of SU2. And what is 2 times 2? Apart 1 plus 3. So we saw that the tree was the way to go for type 2. But now this is a singlet, and we need everything to stay invariant under the symmetries. So this needs to couple to this combination of the two leptons. This is actually antisymmetric, but it's no problem because these are not necessarily the same field, right? We can have, let's say, electron doublet and muon doublet, muon flavor. Okay, so there is no problem there. But what is the charge of S? What is the hypercharge of S? Of SU2, but this, if you want this interaction, you need some hypercharge. Oh, wait, okay. So let's see what happens in this vertex and then see if you can have the other vertex. This is clever. What is the hypercharge of L? Minus 1/2. Depends on the convention. Minus 1/2, no? Is it 1/2? No, I'm confused. It has to be minus 1/2 because you have, we usually write nu L, EL, right? Exactly. You can look at the hypercharge in this way. The electric charge, you get it from the isospin plus the hypercharge. The hypercharge is to be minus 1/2 if we're calling this the neutrino, and this, I mean, you could do it in other ways, but this is the convention. So it's minus 1/2 for this L. And this guy? It's not plus 1/2 because there's the C. Yes, so the double conjugation will also give you minus 1/2. And this will tell you that for this guy to be invariant, so it means I can write it in the Lagrangian, you need S to have hypercharge 1. This was the same for delta, if you recall. Delta was a triplet with hypercharge 1. S is a singlet with hypercharge 1. So now you can answer what is the electric charge of S. It's 1 because the isospin in the usual Gelman-Nishijima relation is 0. Okay, so S is charge. Oh, clearly there is a mistake there. It should be just plus. But then what happens? Yeah, because what we need in the end of the day? We have two Higgses. We need two Higgses to get. You can speak, Matteo, please. You want to get neutrino masses, no? So you need to get a VEV to the neutral components of the Higgs. If this guy is charged, clearly this is a typo, you cannot find a diagram with the correct charges because you cannot give a VEV to a charged field. Otherwise, you would break electric symmetry, electromagnetic invariance. So this is one way to see it. But there is another way to see it. Because when you try to do this guy, does anyone see a problem with this? Even if this were neutral? Even if hypercharges were okay, what is the transformation under SU2? What is it? It's a doublet. of SU2, right? We again have this. And here we have a singlet. So you are trying to make a singlet, you need to, from this, you need to look at this combination. Why doesn't this work? Exactly. Exactly. This is why. So since it's antisymmetric, and it's exactly the same Higgs, unless you are in a multi-Higgs model, this will not be possible. Okay? It means that if you try to take these two guys, so phi is basically phi plus phi 0, there are two components here, and you try to build some combination which does not change under SU2, because under SU2, these fields go to a matrix, unitary matrix 2 by 2, okay, times themselves. To write them in the Lagrangian, you need these matrices to cancel everywhere. What was happening in the type 3 and type 2 seesaw was that you were building an object which transforms with a 3 by 3 matrix which was canceling somewhere else. Here, this doesn't change. S doesn't change at all. So you need this product to be completely unchanging under these transformations. And the only way to do it is to take phi 0, phi plus, minus phi plus phi 0. But these are not fermions, these will give you 0, okay? So in the end, there are only 3 ways to exchange heavy particles. And we only have 3 types of seesaw. Questions? Okay, maybe something more interactive. Have you heard of the Casas-Ibarra parametrization? Sorry, this you will do together. So before, let's see something else. But by the way, show of hands, who has heard about the Casas-Ibarra parametrization? So you will all learn basically a new thing today, okay? So we say that if we know the whole theory, when we integrate out these guys, we will reach at low energies something which is effectively this operator. And we will get a mass for the neutrinos. This is the point of the first exercise. I want you to show that if you integrate out this right-handed neutrino, you get a Majorana mass for the light neutrinos. Okay, so you take this Lagrangian, and integrating out the right-handed neutrino, we get this Weinberg operator. Now, who has some idea how to start at something like this? What does it mean to integrate out a field? Okay, so it might be a bit cryptic what Matteo said, but it's true. If we are using an action principle, our fields you get their equations of motions by the Euler-Lagrange. And the trick here is exactly this. If this field is very heavy, its dynamics are far away from what we can access. So we can neglect this kinetic term. Then we should use the Euler-Lagrange equations to remove this nu r out of the picture. Okay? So the first step I can give you, and the next I will ask you to do yourselves. The first step is actually a bit complicated in the sense that we drop this and you get the rest of the Lagrange. And I'm using some things here which maybe you are familiar, maybe you're not. So you know how to define this psi C? Anyone? Exactly. This we usually call matrix C. And then something missing here? Missing the bar because you need to conjugate, right? So you really need, this essentially, there is a star there, a conjugation. This needs to happen. And you can show that if you have psi c and you do a bar, now this is very boring to do, but it will give you minus c dagger psi transpose, okay? So this you can use to look at this mass term. You write it plus its remission conjugate. I think you can see that this is exactly the same as this, but the remission conjugate, you put bar, you exchange the order. So what I'm doing there is just to write the remission conjugate MR, and we can take all those numbers real, okay? So this is just for one generation. This MR is real. This Y nu is real for simplicity. You don't lose anything with this. And the remission conjugate will give you this. And then I'm using that equation there to write it in this way. Of course, here I made a mistake where this is to the right. No what? Any suggestion how to continue? I mean, we can do it as in the last lecture, we can discuss among ourselves. Feel free. What if we follow Mateo's suggestion and integrate out using the action principle? Okay, this means that we have to use the Euler-Lagrange equations. And it's nice if we do it for this new R here. Essentially, this field is very massive, okay? What do we do in the Euler-Lagrange equations? Yes, so the Euler-Lagrange equations will have derivatives of the Lagrangian with respect to the field, with respect to its derivatives. And if we look at this and derive with respect to the derivative of the field, there is nothing there, no? In this approximation. If you derive with respect to the field, what do you get here? And we treat nu r and nu r star as independent guys, okay? So let's do derivative with respect to nu r. Okay, but in these terms, we just get this part, no? Here it's a bit trickier because this, I mean, these are two stars, it will give 0, but here we have it twice. Okay, so to do it carefully, I'm not asking you to do it carefully, I'll just do it, I'll ask you to do the rest. But if you have this action principle, derivative is equal to 0, and then because of anti-commutation properties of the fermions, you get that this plus the derivative of the transposed guy, if you do things carefully, and this is really a non-trivial step, these guys will give you the same thing, okay? You get this. So let me write it here. And let me know if it's unclear why we get that. I mean, do you feel like you've understood what is happening? Feel also free to tell me no. Yes. Yes, NR, NR, so nu R and nu R star. So when you find nu R C, nu R C is the same thing. And nu R C bar or is like nu r transpose. So deriving with respect to this or to nu r is you have to look at all these terms. This is why it's not giving you one half of this and that's it. You also have to consider that nu r is here. Now I ask you to, I mean, since this is the equation you found, I ask you now to put this back into that Lagrangian, into this Lagrangian here. Okay, you can treat it almost like a number and see what you get. You can group up because we will use groups later. So find the people around you, 2, 3 people, or 4, and try to see if you can come to an agreement. Yes. This is the approximation when the mass is so heavy that, to be precise, you are doing an expansion on momentum over mass, and this is the leading term. So if you keep the kinetic term, the computation will be longer, maybe more correct. You have the propagator, you expand it in powers of p over m. The leading term is what you'll get now, and the other terms will give you operators of dimension 6 and so on, okay, which are like measured in neutrino oscillation experiments of non-unitarity, something like that. So the correct thing is to keep it, but in first approximation you can neglect it. Yes, which is not a mass eigenstate, but if it's large enough, we saw that we have two mass eigenstates. One which is basically this one. You remember Claudius saying, basically it's the other one is like 10 to the minus 12 contaminating. So you can treat it like this. Which one? The middle is just the Lagrangian without the kinetic term and the standard model part. Yes, I use that guy. And the emission conjugate. Do you have some questions? Did you get this? I mean, it's just to pass it. What is this? What is this? You see it there, no? Okay. So you found already psi r c dagger, which is minus psi r t c dagger, just from inverting. Now, did some of you find new r? I'm just copying this. Let me restate that. I mean, this is a number. It's the Yukawa coupling. This is also a number, but now with dimension. And these are the fields LL and phi, right? This is just from solving this equation for this product here. Does anyone have an expression for r? Because the whole idea, right, is to put what we find from this equation, put it back here. We can directly use, let's say, new RTC dagger. This guy, we just found out what it is. And this is the emission conjugate of this. So it would be nice to know what these new are. This is also the emission conjugate of this. So you can save trouble. You don't need to compute new R bar. You just need new R and this new RC bar that we just found. So what is, did you find new R? Give you some couple of extra minutes. Anyone? Ideas, come on, because maybe I'm rushing you a bit, but I think we can find it from what we have, no? Yes. Maybe you have a lot of, however, a lot of effort, so we can start already from this one. Because then you just pass the C to the other side. But why can you multiply C to the right? No, in the sense that why is it useful? Because it's unitary. Okay, so this is a non-trivial thing. The matrix C is unitary. Okay, so C minus C dagger is its inverse. So you can do this. You can multiply by C both sides and transpose everything as Matteo is saying. And what do you get? These are just numbers. What do you get? Higgs? Okay. There is another property of C, which is C transpose is minus C, okay? Yes. Oh, thank you. You're right. We did not, sorry. Feel free to ask the question. Because you're right, this is missing. Yeah, don't think you are stupid. If it's not working, ask why. Because I don't want to rush steps. is minus C, no? This number is always there. And we get, yes, so this is a number, this is a scalar, this has Dirac indices only, it can pass through here, it's blind to all of this mess in the middle, and you use that relation, this definition, and you see this is equal to minus y nu over mr phi tilde transpose LC. Okay, so this is what you get. And now you can put these things inside. Maybe I will not bore you with doing it by hand. Just try to see first and try to understand what happens. No? We put it up. Let me go back to this guy and we have it written there. We remove nu r here and you get something that is like LL bar, phi tilde was there, and then phi tilde transpose LC. This is the emission conjugate of this. We just write plus HC. Here you get again L bar psi tilde and again psi tilde transpose LC. So you get something which has in your Lagrangian how many fermions? No, I mean in this term and in this term you'll have a very similar structure when you replace nu r and this rest by this thing here or that thing here. 2 fermions in the term, 2 lepton doublets. And how many scalars? 2 Higgs doublets. So this is the Weinberg operator. It's a very nice derivation because you didn't care about matrices, we just did one generation. But if you put things back in the Lagrangian, okay, and hide things in HC, something interesting happens. Here there is no 1/2 factor. Here there is a 1/2 factor. Here there is a suppression y over mr times the y that was already there. Here there is mr and the square of y over m. So it turns out that you cross one of the m's here and both terms are the same up to a factor. The result is a 1/2 factor and the coefficient is what you expect from the diagrams. Have Yukawa squared over the mass. Okay, where you identify this, you look at this and you say, this is a Weinberg operator. Aside from all the transpose and tilde and, I mean, 2 lepton doublets going in and 2 Higgs doublets going in. And there is a 1 over mass scale here that you identify with the scale of the heavy guy. So this is the Mariner mass term, which after electric symmetry breaking gives you neutrino masses, as we've been discussing. What happens is the Higgs gets a VEV and you get 2 terms. Okay? And you can write this, I wrote explicitly the emission conjugate because in the lectures Claudia has been using these spaces where she puts new LC to the right, but here for the exercise are consistent with these other bases. Okay, so essentially the difference between the lectures and this series is that in my Lagrangians I will get an m nu, which is the conjugate of Claudia's m nu. But here, one generation, no problem. We'll consider this guy diagonal and real, so this will not affect things much. But if you work this out, if in the future you need something to look back at the seesaw, you'll see why this different, maybe the differences are there. In the end, however, no matter the convention you choose, every physical observable should be the same. Okay, questions? Yes, if you take the path integral, there is a formal way to do it where you really do an integration over all possible field configurations of these right-handed neutrinos. Okay, of course, this is too much for this. In fact, this is a very simplified version of what you do actually, because you will find papers where you don't neglect the kinetic term. And as I was telling your colleague, if you don't neglect the kinetic term, you'll have around not just m's, but the momentum of this guy, because this is I derivative gives you the momentum. And you will get an expansion in the sense that this mass is so large that the energies and the moment are small. You get an expansion in P over M. And the leading term is exactly this that you've just found out. It's the Weinberg operator. Okay? But if you keep on doing this expansion, you will find that there is a dimension 6 operator, for instance. Yes, where the derivative of this of the Higgses or the leptons appears. So still it's a low energy effective operators, only with standard model fields like this one. But it has a derivative, which is another mass power in the top part. So you need another 1 over lambda, and you get something which is suppressed by 1 over lambda square, which is the dimension 6 operator. But this, just to mention, this kind of effect you can see maybe in violations of unitarity when you are testing unitarity of the PMNS matrix in, let's say, Dune or something like this. But this is not the main effect. The main effect of these kinds of things are neutrino masses. This is why the seesaw is invented. Is it clear? Okay, feel free to ask questions anytime, but now I'm going to put you again in groups, and we'll do a bit of a race to see which group can give me an answer first, because we're going to derive the Casas-Ibarra parametrization, which sounds scarier than it looks. You'll find it in many papers of theorists, and also to confront with experiments. How do we start? We start from the more general setup with 3 generations. So now I just put indices in this previous Lagrangian, and instead of a number y and the number m, I will have matrices y nu and mr. And I mean, this is in these conventions, the transpose is here. This is the light neutrino mass you will have. Okay. There is a minus sign. Maybe it's a result of conventions. But the mass matrix of the neutrinos is not a physical thing. The mass is in the mixing R's. So don't worry if you see some people using a minus, some people not using it, some people having a transpose here or there. As long as they are consistent, you should be okay. And for simplicity, let's talk about a basis where charged leptons and right-handed neutrinos are diagonal. So they have definite masses. The only thing that has a non-trivial structure is not a diagonal matrix, is this y nu. And now you should try to discuss together and show that the matrix which has the masses in the diagonal, that Claudia also wrote today, can be written as a product of a matrix by its transpose. Go. I mean, first one to give an answer wins. I don't know what, but recall how D and M nu are related, by the way. And since Claudia's conventions are different, I actually have to give you how they are related. Oh. So in my convention, since my matrix is conjugate with respect to Claudia, I conjugate her whole equation. So if you go to the lecture and take the conjugate of both sides, the right-hand side was the D, it stays D nu, which is this matrix that is there. But now this left-hand side, instead of U, P, M, and S dagger, it's just transpose. And instead of U star, it's just U, okay? And I'm writing PMNS because I'm telling you that charged leptons are diagonal. So U, PMNS is UL dagger U nu, and this I'm telling you it's 1. Okay? So using this relation, show, and the fastest group can then come to the blackboard and just write this product. Show that this guy is the product of a matrix and its transpose. Yeah. Yes. let's call it big M1, square root of big M1, square root of big M3. Okay, so are you following the how your colleague did? He took this equation, he inverted it for d nu. Okay, so sorry, he took the equation I had here, he inverted it for d nu, and he's now writing m nu from the seesaw formula. And he's identifying that if this matrix is real and diagonal, he can, okay, he can also write it like the square of this matrix, no?
Yes.
Go ahead. This matrix is the square root of the other one. Yes. There is a square here. Mm-hmm. V again. Yeah.
And this remains the same because it's diagonal.
Exactly.
So it's and still I miss this. So at the end, this is a transpose.
Yes, let me put the V, you put it here? Okay, I put it here.
Yeah, exactly.
Yeah. Why do you miss a sign, but essentially everything is correct. So you recognize that the matrix is something times its transpose. The minus sign you can get if you do what?
If I put the imaginary part.
If you put I.
Yes.
If you put
Imaginary units.
yes, so if you put I there, you just absorb this, which is I squared. Great.
Now we miss some.
So 1 point for your group. Then you should ask the organizers what the points can buy you. It's exactly this. You see the I, the V that your colleague had. This dr minus 1/2 is this matrix he defined here. And the PMNS and the Yukawas. So you just shown this. Now you can try to go to the second one with this knowledge, to the part B. Use this result to define a matrix R which is orthogonal. Can be complex, but it is orthogonal. What is an orthogonal matrix? If I have a matrix which which is orthogonal, which equations does it satisfy? Yes, an orthogonal matrix is a matrix which times itself, transpose, is equal to the same thing as if you do it in the other way, is equal to the identity matrix. So the idea is just define a matrix R. This should be very direct from what you have here, which is orthogonal. It can be complex. Nothing about being real here. Actually, this you don't need to, I mean, I don't know. Do you have any ideas? If you want, you can discuss among yourselves, but if you have any ideas, feel free to speak up. Are you ready for a second point? So what is the matrix R? So let me see. Let me see how I defined it, if I took R or its transpose. So let's take the right one, okay? And then what do I need to do is, because this is not yet orthogonal, what should I do? Can you repeat? To which side? When you have this, right? Your colleague is suggesting to divide d nu, since it's diagonal, as the product of two matrices, which are the square root, no? D nu is m1, m2, m3, so it can write as square root of m1, square root of m2, square root of m3, squared, no? So if you take this equation and on the left, but we want to do the same thing to these two guys, no? They are the transpose of one another. Exactly. So we divide this into the square roots, and then we multiply both sides by their inverses, which appear like this. So we defined what is known as the orthogonal matrix of this Kazi-Ibarra parametrization is just this one, where d nu, okay, it's 1 over square root of m1, 1 over square root of m3, and the other one was the inverse of that one. So 1 over square root of big M1, 1 over in the diagonal, 1 over square root of big M2, and 1 over square root of big M3. So this is straightforward, but now, now what do we want? We need to write, this is the final step in the Casas-Ibarra parametrization. This is a very well-cited paper, okay, by Casas and Ibarra, Alejandro Ibarra, which has many citations just for figuring out this way to write in the type 1 seesaw. The Yukawas. So now use these results to write y nu in terms of R. I mean, this, anyone, just take the chalk and do it in 2 seconds. You just need to use this, no? Yes, it is as straightforward as it looks. If you're wondering if there is something hidden or complicated, just products of matrices. But it's actually a nice formula, as we will soon see how to interpret the different components. If you don't want to get up, I mean, can someone tell me what they're getting for y nu? Okay, so what do we get? I mean, it should be straightforward. As you are saying, you just multiply by the inverses until you dig out y nu from there. Okay, so there is this 1 over IV or minus I over V. Yeah, we need to cancel that dr to the minus 1/2. Okay. Yeah, so in this right-hand side we had R, right? On that side. Plus 1/2. Okay. 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 What is U? What is dr 1/2? Okay, which is like big one, M1, big M2, etc. So if it's 1/2, it's a square roots. And here it will be the light ones, no? Is this clear for everyone? Because, I mean, this is very widely used, and now we should understand why people like this very much. Because, I mean, what do you measure in an experiment? Or where are the parameters? What do you measure in neutrino oscillation experiments, in colliders? Sorry? Yes, asymmetries in processes. So you compute rates, you extract from those, let's say, mixing angles, CP phases from the asymmetries. So you extract, let's say, from experiments theta j that are here, the delta phase, and maybe if we are very clever, not just from neutrino solidity case, something else, maybe also the Majorana phases. So PMNS is full of things we measure. We also measure what here in this expression? What do we know? I mean, we know V, okay? We know the neutrino masses. Okay, we know the mass square differences. So it's not that we know all these, but maybe with cosmology, etc., we can maybe one day know all three neutrino masses. Maybe with Juno we find the ordering. So these things are masses, and also these things are masses. So if your type 1 seesaw is not at crazy scales, maybe it's at low scale, maybe one day you could measure this. So this is a way to write the Yukawa matrices in terms, or the Yukawa matrix, in terms of masses, things that you measure in oscillations and lepton violating processes, up to this R. So this matrix R, which is orthogonal, you can parameterize it. It's not a general matrix. It's a bit more specific because it's orthogonal, but it's a known. It depends on what happens with. I mean, these Yukawas are the interactions of the right-handed neutrinos, which are heavy with standard model particles. So this R encodes information that we don't see at low energy. It's kind of, if you do a fit of the seesaw, this R is you vary it and try to fit the data. But all the rest is fixed. So it's a nice way to parameterize the Yukawas, and you will find this in any paper with type 1 seesaw trying to confront the data. Okay, so this is known as the Casas-Ibarra parameterization. And I don't know if I have, okay. I had a very little exercise which we will kind of skip, but let me know if you have questions before. Yes, sorry, this is the Majorana one. So these masses, we don't know anything about them. If they are, we don't even know if right-handed neutrinos exist. But in the seesaw one, these are the masses of the guys. More questions? Okay, if not, let me flash a bit the last point, which we'll not do in detail. But I mean, it's to show that the Majorana mass matrix is symmetric. Just leave you this here, and if you are interested in knowing why, because we always say it's symmetric, why it is symmetric, it's a bit of Dirac algebra. So this is the usual psi bar. Okay, this is the definition of psi c, which is, I had it there, it's c times field bar transpose. This is the field bar. I expand a bit just to show you how this bilinear looks. so that you can prove, if you want, that if you have two fermions, psi and chi, this guy is equal to the guy where they exchange. And this is the key to proving why nu Ri, nu Rjc with a bar there is exactly equal if I change, keeping the bar in the C in place, if I change these two guys. So this is the reason, the algebraic reason why the Mariner matrix is symmetric. If you have something antisymmetric, it will vanish, okay? And now we move on to the type 2 seesaw phenomenology. Okay. Where I'm giving you again the type 2 seesaw Lagrangian that you have seen in the theory lectures. So now forget type 1. Suppose type 2, meaning that there is a Higgs triplet of high mass. So it's something which is not no color, but is a triplet of SU2 and has hypercharge 1. As we saw, we need hypercharge 1. The relevant Lagrangian is the one we also saw together. No, you have to have delta coupling to two else, either in this way or the emission conjugate, and phi's coupling to this delta. And I also put here a part of the scalar potential. So this guy will have a mass. This is all that the last term is telling you. Delta has a mass, and it couples, as we know, to fermions and to the Higgses. This is a convenient way of writing a triplet because you look at this and you think, where's the triplet? I expect to see a vector of three fields. A vector with, delta plus plus, delta plus, and delta 0. There is a trick which is kind of to rearrange the Lagrangian and write, instead of using this vector, you write this vector with the Pauli matrices, which will have some nice transformation property, and this would be too much to derive here. But in papers, you'll often see no mention of this triplet. You'll just see Lagrangian written like this, and delta is a matrix which contains these fields. The point is, it's the same Lagrangian as if you were to write with a triplet like this. It's just, don't get scared. It's a way of writing it in a different manner that it does not, it's not obvious. Okay, it's not obvious at all that you can write it with this 2x2 matrix. But it is enough to see what we want, and it will appear in all papers. Now, in this type 2 seesaw, how are the Yukawas and the Mariner mass matrix related? Think of the diagram. Let me draw the diagram, by the way, and you tell me what are the couplings that come here. This is again the type 2 seesaw Lagrangian, right? Sorry, diagram. So we saw what happens to type 1. We are collapsing, as in the Fermi interaction, we're collapsing the heavy degree of freedom because there is a propagator, right? So this propagator, what kind of factor will it give you? 1 over the mass squared, no? If the mass is too heavy, at low energy, you will never see any effect beyond this. What are the couplings? Can you repeat? Y delta and mu delta. So this one is Y delta, Ij, and this is, so Li, Lj, and this is mu. Now, from this, if you imagine that you contract this into the Weinberg operator, what is the expected value of this diagram, of the Weinberg diagram? After electric symmetry breaking, which, as I told you, this is the neutrino mass matrix. Mu, Y delta, Great, yes. And where are the indices? Yeah. So what can you tell me with respect to the type 1 seesaw? I mean, this is not actually equal. Sorry, it is proportional because we're just looking at the diagram. Um, Claudia did it in the lesson and she wrote the exact expression. If you use her V, it's like equal to minus this. If you use my V, which is 174, hers is 248, you'll get a factor of 2, okay? So, sorry, 2 here. But that's not the important part. The important part is to understand the dependence in this mu, in this y's, and in this mass. Of course, if the mass is heavy and extra heavy, you will suppress the neutrino masses, so this is why it's a seesaw. But what can you tell me that differentiates this a lot from the type 1 seesaw? Which we just saw the formula. This is type 2. And the formula for type 1? Sorry. Differences. Huge screaming difference. Sorry? Look at the indices. Yes, so this is proportional to the coupling squared divided by the mass, and this is proportional to this coupling times this other kind of coupling divided by the mass squared. So it's a bit different with the v squared. But what about the indices? Because I didn't write them here. Sorry? Yes. The indices here are contracted. No, we have a matrix product. Sorry, KL. This is symmetric and LJ. So to compute this mass matrix of the neutrinos, here you have to multiply 3 matrices. And this is why we are finding that there is this huge redundancy in the Casimir parameterization. Because these are the Yukawas in the type 1 seesaw. If you measure all the masses, or the, let's say in some sense, probe this mass matrix, you are probing the product, so you don't know what is y nu. You know what is I nu up to a orthogonal matrix. What about for type 2? I mean, up to these factors, no? The flavor structure is completely determined by that matrix. There is no matrix product. So the relation is really that they are proportional, these matrices, okay? Which is not the case in the type 1 seesaw. In the type 2, if you measure, let's say, neutrino masses mixing and so on in certain bases, you are actually measuring the flavor structure of the high energy couplings, which is kind of neat. All right, is it clear? So there is a part B, which we'll close the lesson with part B. But now I wanted to ask you before the C and D and E. Namely, that if you have these interactions that we added, you have neutrino masses. But what else? Claudia told you that neutrino masses delta L equal 2, you are violating lepton numbers. So in principle, you can have also other processes that violate lepton number. This is not the case for this process, but they violate charge lepton flavor. So she told you that you can have in neutrino oscillations, you can violate, let's say, LE, L mu, and L tau. Because you start with a neutrino of the mu1, you end up with neutrino of the electron. The individual lepton numbers are not conserved. But then she told you also that if you compute it in the standard model, you will get nothing relevant, 10 to the minus 50 for, let's say, mu 2 gamma. This was maybe the first lesson or the second lesson, where she told you even though we are searching for it, if it's just a standard model with neutrino masses, this is very slow, very, very low, inaccessible. But if it's a type 2 seesaw, and if these new fields are light, this can be relevant, this can be large. And we can see this through diagrams. So I want you to draw, or tell me how to draw, the leading Feynman diagram for these processes. Let's start with mu to 3e. How could I draw a diagram from mu1 going to 3 electrons, positron, electron, positron? Yes. Perfect. So if I understood correctly, you have a new interaction, which is this mu e, and then the arrows are like this because of the form of the term, going to delta. But if I understand correctly, you're now suggesting delta couple to 2 electrons. Yeah, so we do this again. Okay? So this is a way to get mu to 3. This, of course, if this guy is very, very heavy, this will be very, very suppressed. So it's not true that you will expect this signal in general models, very simple models, but it could be that this guy is at low scale. For some reason, like you were exploring today, these coupling constants help you get light neutrino masses. And then you can have this maybe observable at Bell or at PSI. All right. What about mu2 E gamma? Can you find one diagram with mu2 E gamma? I mean, there are several, so we can rotate. One of you can come and draw it, then another person can come and draw it, if you find them. Recall also from the lecture how it was in the type 1 case. Maybe it inspires you. Okay. all these particles are charged, so the photon is no problem, right? To get to the mu 2e gamma, the hard part is mu 2e. So you have the doubly charged delta. What do I do with it? So a neutrino and a charged lepton. Sure, I can couple, but it will be something like this. And here, let's say an electron and a neutrino. But I need mu 2e gamma, so where is the mu? So there should be a mu coming in, no? Electron coming out. A photon will also come out, so let me draw it like this. But here something is missing, and I have an extra neutrino. No need, no. I mean, yes, there is a loop, but which loop? No need to complicate too much. No, you have the neutrino, so you can just do this. I mean, I know it's not very easy to see it this way. I will draw it in another way. But also from this, you can close here. The mu 2 gamma involves just closing off one of the legs that you have extra, no? There are several diagrams. One is just closing up this. One is just closing this. I mean, your colleague found this one. Let me be a bit more, draw it in a nicer way because it's a bit ugly. Let's just do a line. We do this delta plus. I mean, this is mu, this is the neutrino, and this is the electron, okay? And the photon. And we need to couple the photon somewhere, and it will not couple to the neutrino. So it has to be somewhere here. This is the same diagram. It's just a bit uglier that way, but we managed to close the loop. No. This is a good question. No, because when you do this, you can couple, that first coupling will tell you, okay, mu1, nice, electron, nice. Oh, but there is delta here. So if I want mu 2e gamma, I need to not have mu 2e gamma and delta, I need to close it. There will always be a loop. I also draw this one better. So this is one possibility, no? And which neutrino do we have here? Yeah, so in some sense, we have all of them, right? Because we can consider the massive states, which here couple with y delta mu kappa, okay? And this will couple here with y delta kappa e, or alpha. I mean, the point is that you will sum over all possible propagating neutrinos. In that diagram there, is it the most general one we can write of the type? I mean, let me write it nicer again with just one line. Mu, there is E, there is a loop. Now it's delta doubly charged. It can couple to a photon. Either here or actually here. So here, there is, if I close the electron loop, I can do like this. No? This is the same diagram as above where I closed, and I added a photon here. There are two actually diagrams which I can have because I can add the photon there, right? So I could have put it there instead. As you prefer. There are two topologies of diagrams. And are we done? There is a bit of a variant of this diagram. Can you find it? Not topologically different. It's just a small difference. If delta is neutral, actually, if you expand that with this matrix, you'll find that it will collect the neutrinos. So this is a very good point. If you expand that, you'll find that delta neutral couples to neutrinos. Delta plus couples to a charged lepton, let's call it E or L, and a neutrino. And delta plus plus couples with two charged leptons. So you can have those couplings, but they will not give you mu 2 gamma. The mu 2 gamma will be either this one, which is this kind of coupling, or this one, which is this kind of coupling. But we have not exhausted our possibilities here. What coupling is this? Up to factors of 2, etc. I mean, if you look at the Lagrangian, it's still y delta. Which element of this 3 by 3 matrix enters here? 1, 2 if it's electron and muon. The muons always have to have it here. So, and it's symmetric, by the way, because the Majorana matrix is proportional to y. So if the Majorana matrix is symmetric, as we've just shown, also y is a symmetric matrix. In fact, you see here a numerical example which is symmetric. Does it need to be an electron here? Yes, it's the same thing. But we have other possibilities, no? Just to say that we can have anything here, E, mu, or tau in the loop. Because we can have this. So running in the loop, we don't care. You can have every flavor. You can probe basically the second row or second column of y delta. Okay? Now, we are a bit running out of time. Let me know if there are some questions. Yes? Yes. This is a good question, but I don't know the answer. So if we take into account the relative masses of the fermions, of the electron, muon, and tau, what is the phase space effect? Because I didn't work out the chirality. But there should be a difference, yes. Now let's assume there is no difference. And let's compute a branching ratio, okay? So you found out which couplings are relevant, essentially, and you found these diagrams, no? So the photon either couples to the delta or to the charged lepton, which can be anyone, varying here. You found also this one. And that is the diagram for the mu23 that your colleague found. Just put this leg in this side, no? You have mu1, 2, 3 electrons. Okay, but now let's try to compute something. So let's assume this is your mass matrix. And we want to compute this ratio of tau going to E over tau going to mu E. Sorry, mu E. Let's assume that there are no differences in the masses. I mean, they are small. So how, this way all your phase space will not be important. And in this ratio, everything will cancel except couplings, no? Let's look at the diagram. We have this diagram again. Not closing. Tau to E or tau to mu E plus E minus, which would be something like this, no? So either E or mu. If the phase space is all the same, what is this ratio? Exactly, the square of the amplitudes. The amplitude is proportional to coupling, so the final state with the mu and a final state, sorry, with the E. Essentially, all the phase space will cancel. What are these couplings? Yes, so there is always, let me write this better, tau to E, tau to mu E. There is always this first coupling, no? Tau to E. It will cancel. Does this make sense? Okay, what about the other two? You said it, right? Yes. Ah, yes, but this is why I put here mu plus. In fact, let me do it correctly because here I have tau minus, sorry. Let me do the arrows correctly. Because the arrows always either clash or go away in this kind of vertices. But you're right, thank you. So this will be, no, this will be E minus. And this is plus plus, okay? Because the arrows tell you the fermion tau minus going out, so it's a tau plus going in. And here you'll have E plus and mu plus. So you always need this guy here. Actually, I think there is a symmetry factor. You are right that there is a symmetry factor in the case where there are two electrons. No, somehow it's the same symmetry factor because in both cases. No, wait a moment. I have to think about this actually. So maybe up to a factor of 2, as in all physics. But the point here is that there is EE and mu mu. And you can compute this number if I give you this mass matrix. How much is it? Maybe I did something wrong. Wait a moment. So, sorry, this is wrong. Am I also wrong in the diagram? Because maybe I did the wrong question. Anyway, you see, if it's it's this kind of ratio, maybe with a symmetry factor. Probably there is a typo and there are signs that are different, but essentially you compute the ratio of y's. Now, if I give you the mass matrix, you know how much the ratio of y's is, no? This is type 2 seesaw. So they're proportional. So, okay, let me just, maybe there are typos here, you are free to check. Probably I should have put a minus here and something else, but you will compute the ratio of Yukawas, and this will be the ratio of elements of the mass matrix because the type 2 seesaw, they're proportional, right? Does it make sense? I mean, I admit I probably made a mistake here, since now I'm looking at the diagram and I'm finding that it's a different ratio of couplings. Maybe there's a factor 1/2. The key issue is that you can compute, if you have a model, compute these ratios, which you expect to observe maybe in Bell or something like this. Okay. Questions? No, I think there is a mistake here. I mean, you see, if this were true, then you can just take the element e tau, which is this one, and divide by this one and square. This one is this one. So in this example, it would give you something small. The whole point is that if somehow your model gives you a very specific mass matrix for the neutrinos, and theorists have a lot of fun inventing ways to constrain the mass matrix, but they should give you some prediction for something you can measure. And usually it's something like this. It's something which is very straightforward in type 2. But I want to put you in the computation of something, do the computation of something. So let's estimate this branching ratio, okay? What is the branching ratio for mu to 3 in the type 2 seesaw? In general, let's compute it, and then we'll see how our experimental limits will constrain our mass, our framework. What do I need to do to find this? How do I define this? Okay. How large is this in terms of branching ratios, the decay to the usual decay of the muon? I mean, what is this? Yeah, so this, no? Yes. If you think of the diagram and you neglect all the masses, the phase spaces will cancel up to maybe a symmetry factor. Let's do an estimate. Okay. So as you say, there is the GF squared. While here, we just saw more or less what are the couplings that enter. So what do I write there? Okay, so it appears here. It appears here. So it's squared. Is it the same element? Wait a moment. So this mu2,3 have these couplings, no? They're not the same coupling. So what do I get here? I mean, what is the amplitude that we saw the amplitude, no? The amplitude, let me write M, is basically Y delta. That coupling times Y delta. Which Y deltas? E mu and EE. And what else? What else is here that is important? Exactly. Squared. This is the amplitude. So if I want to estimate the decay rate, I do this. Now, I tell you that assume all the Yukawa couplings are order 1, which would be very nice. It would mean that we can have strong couplings. Uh, how much is this branching ratio? Or order of magnitude? Yes, so order 1 couplings. This means that you can not think about these couplings. I could write them here, okay? Modulus squared of the first times modulus squared of the second. I'm just saying they are equal to 1. And then I get just GF. No, but it's a branching ratio. So if it will appear both in the decay of the mu1 to 3, because if the electrons are light enough, and they are like neutrinos, which are mass. So this m to the 5 will cancel mu. And you will get m delta to the 4 in the denominator, okay? So if you are at PSI and you aim to go to these values, actually they are trying to consider to reach these values with this experiment mu3. What kind of, assuming that the couplings are order 1, what kind of masses are you probing? I mean, you just invert this. No, you say if the branching ratio is of the order 10 to the minus 16, how much is m delta? I'll not bore you with the computation on your calculators because we're running out of time, but I can tell you. Yes, there's GF. With the square roots. With the square root in GeV. Very good. So 10 to the 6 what? So essentially you are probing scales of the order of 3000 TeV. Okay? What does this mean? I mean, you cannot expect to produce this particle delta in a collider, right? If it is 3000 TeV. But you could see it in intensity experiments. This is why people so often talk about the complementarity between the energy and the intensity frontier. The intensity frontier, you look for rare processes like this. You look and you look and you look, and you can set bounds on rare processes. That will translate into bounds on your theory, which maybe you cannot get with a collider where you try to do this resonance appear, okay, out of the diagram. Clear? Okay. And now a bit of programming. Well, I'm afraid that since we have so little time and you are probably all very tired, yeah, we can just look at this together. I'll try to, you will ask the questions and I will give as little detail as possible, so the opposite of a lecture. But you can ask me why things are happening. So again, we're still in the type 2 seesaw. I'm going to tell you that I have this mass matrix. God knows where I got it. I'm a crazy theorist, so I come up with these models, okay? And the key thing here is that if a theorist gives you a mass matrix, you should be able to extract the masses, the mixing angles, and so on. This is something that Claudio told you in the first lectures, but it would be nice to see it, I mean, really in action. So the exercise is to compute the masses, the mixing parameters, the delta. I'll show you how to do all this, and then even the Mariner phases. And you can compare, you start by thinking, okay, mixing, I know the PDG gives me PMNS is this very nice expression where I can take the angles. But how do I go from M nu to U? This I have to do numerically. So, funny thing is I have it here. You can do it numerically with Mathematica, some other software. I mean, you just really do a diagonalization in a sense. But the problem is that, as Claudia also told you, this is not a a standard diagonalization that you learn in linear algebra. No? I mean, this matrix M nu, I told you before, in certain conventions, it's like this. We are assuming charge leptons are diagonal, so this matrix nu, u mu, will actually be the PMNS. This is why I'm not writing the nu. In linear algebra, you take a matrix which is like a normal matrix, so Hermitian, something like that, which you know you can diagonalize with a unitary matrix. This is not the usual diagonalization. If you want to be very technical, mathematicians know this as the Otono-Takagi decomposition of a symmetric matrix. So we know this is a symmetric, and we don't know anything else. It's complex, but symmetric. Mathematicians will tell you that you can do this. But if you really want to find u, as Claudia told you, it is nicer to just work with some matrix which you can just ask for the eigenvalues and eigenvectors. Okay? So what is usually done is you multiply this by its own conjugate. So let me conjugate this. I call this D again. If I conjugate this, I get U dagger, M nu conjugate, U conjugate, and I can multiply, and I get D because these are real. Okay, I multiply this by itself, so I get a square. As you saw also in the lecture, I will get U dagger, M nu, M nu. If I multiply this one by that one, this U star will cancel the U transpose. You'll get this, and then U equal to D square. The Majorana mass matrix is symmetric. So this is Hermitian. And then linear algebra helps you. Okay, because now you know a Hermitian matrix, I just ask for the eigenvalues to find the columns of this matrix U. So you do this numerically, and then you find, I have these eigenvalues. So unfortunately, I don't have them printed here, but you have the columns of U. You have to check, as Claudia told you, that when you multiply, when you put this U there, you will get the three masses which are positive. I mean, if you have time, I urge you to try to do this exercise and ask me for questions if you are not being able to get this, because it's really, there are a lot of pitfalls. First pitfall is that you don't do this. You should not go looking for the eigenvalues or eigenvectors of M nu. You should always look at this product. Second pitfall is that once you find the three columns that are here, you must make sure that you get three positive things. Third pitfall, how should I order these guys? Let's say Mathematica tells you, you have three eigenvalues of this matrix. Okay, they are, yeah, actually I have this here. Maybe I can project the solution. Sorry. So, but do you know how to order the eigenvalues? Yes, so if I have three numbers which are from lower to higher, if it's normal, what do I have for M1 and M2 and M3? Go ahead. Right. So if you have the three, it's directly the same. Yeah, but if it's inverted ordering, don't forget that our D is defined in this way. So you have to put the smallest one here. You have to always keep this order. Okay, this is something that is not obvious, even if M3 is the smallest. Okay, so solutions. Let's see if I can show you this. Oh, too far. Okay, so Mathematica gave me these three numbers, these three columns, which are eigenvectors of m dagger. I have to check if I need to multiply by some phase these columns. And Mathematica also tells me something like the eigenvalues are these numbers in electron volt, okay? In this case, you see that two of them are very close together and very separate from the third, so you can guess that this fits very well the normal ordering spectrum. If, however, this is not the most general thing, if you have some way to change these parameters in your model, it could be that you find a scenario where the two heaviest ones are closer to each other and the lightest is not, and then you have to not put it like this, but yeah, okay, I hope it's clear, even though it's something that you will only understand if you do it once in your life. I mean, to be comfortable with. Now, here it's NO because the two lightest mass are closest to each other. And you can unambiguously say that M1 is this, M2 is this, and M3 is this, the values that they give me in order. And you check that this matrix is the one that correctly diagonalizes. So as I told you, you need to create U with eigenvectors and order the columns such that you get the correct order. Point, another pitfall. This should be normalized. Why? Right, so Mathematic will not care, or maybe other software will not care. It will give you the eigenvectors up to a constant. You should always normalize them so that the matrix you built like this is unitary. Now, okay, we did the hard part. I mean, we have the matrix here, we have the masses, we have delta m squares, everything is fitting. Okay, now I try to get the angles. You learned this in the lesson, no? If you look at this matrix right here, you will be a bit shocked if you just try to compare, because this is a real number, this is not. And I told you in the other lesson that there could be unphysical phases. So how would I read off the angles? Let's say theta 1, 3. Yes, you can assume, so you can rotate. Yeah, you can consider there is some phase which cancels this, and you make, let's say, this real and this real. Yes, you can do this. It's correct. There is another way to do it, which is bypasses the trouble of finding that phase and gives the same answer, which is to look at the modulus, the absolute value. Yeah. Then you directly are sure to get sine theta 1, 3. So take the absolute value of this number. It should be exactly sine 1, 3 absolute value. Okay. Since the angles are parameterized between 0 and pi over 2, it's positive. So this is how you get theta 1, 3. And to get theta 2, 3, Claudia told you to look at this, also the absolute value, and compare with the absolute value of this. Theta 1, 2 here. You can even use, I don't remember what I used. I think I computed the cosine. Once I know the sine 1, 4, and 3, which is this absolute value of this thing here, I compute the cosine, and you see that I can just divide this and get the sine of 1, 2, and here the same thing for sine theta 2, 3. So is this clear what is happening here? The angles are quite direct, no? Okay, what about the CP phase? Yes, so you learned in the lecture that there is this JCP, the Yarskog invariant, which is sensitive to what quantity? Yes, so it has sines of all the angles and it has sine of delta. Let me see if I can show you this. Oop. So JCP, actually, it's interesting because we've seen, if there are two neutrinos, there is no CP violation. If there are three neutrinos, there is only one CP violation quantity in the Dirac case. This makes sense with what we know. There is just one Dirac phase, okay? But it's interesting that you can just go to the PMNS, take any sets of 4U's, as we discussed also the other time, and these products will cancel all unphysical phases, and they will all be proportional up to a sign to this JCP that Claudia defined. I mean, you can, JCP is the imaginary part of this, but you can also choose other alphas and other J's. You'll get JCP up to a sign. Okay, so just be sure if this sign is correct in this relation, and you can just compute it because you know the PMNS numerically. You know that this will kill all the unphysical phases, so you don't worry. You get JCP. And as you were saying, JCP is the product of all these things. So either write with the cosines or sines of double angles, whatever. But you know all these things also, so you extract sine of delta. Okay? Questions? How do we get? But do you know delta? Yes, but before this is correct. So to get the Mariner phases, we will look at other invariants. But we have not yet found delta. We found sine delta. Just how do we get delta? Yes. But delta varies between 0 and 2 pi. If sine delta is 0.3, yes, there are two possible values of delta, which is 0.1 pi and 0.9 pi in this numerical example, okay? So to disambiguate this, you can compute some other matrix, element of the matrix, okay? You need to look, for instance, at, I don't know, this one or this one. You know all the angles. You test the two values of delta, and this way you can disambiguate, okay? It's just, it's important to disambiguate. So if delta is 0 pi, it's CP conserving. In this case, if you compute things, you will find that it's 0.2, sorry, it's 0.6, the absolute value of this, which only works with 0.9, so you extract delta in its cosine. Okay. Now, going to the Mariner phases, you were saying we need other invariants, right? Can you guess which ones? Yes. No, okay, but the 1, 1 element, yes. And if we think of the matrix having, sorry, I know you all want to go. If there are unphysical phases here, and this is the PMNS matrix and Dirac, and we have the phase EI delta, sorry, eta 1, EI, eta 2. This will affect the first column, and it will affect this element here, but there can be an unphysical phase here also, okay? This one will affect the whole row. So how do we get rid of it? Let's say I have here some EI alpha because I rotate charge lepton the electron. Maybe this is a bit too schematic. Let me. So if there is this phase alpha to the left, the full PMNS will look something like, I mean, there are the cosines, this EI eta 1 plus alpha, right? Cosine sine EI eta 2 plus alpha. sorry, sine theta 1, 3, E I alpha minus delta, and the rest of the P-minus matrix. So I want to capture the Mariner phase at the 1, right? But I want to capture it and not worry about unphysical phases like alpha. What should I compute? I know everything else. I know delta, I know all the sines and cosines. Okay, I can take alpha from the third one, and then I put it here, no? So that's the reasoning behind doing this product. U, 1. Sorry, just a moment. U, E, 1, U, E, 3, star. With this product, you achieve the same results. You are basically canceling the phase alpha. So you don't need to go through the computation, but you'll get the same results. And for the other Mariner phase, trivially, okay. So this is one of many choices, the simplest one, okay? And so you compute these two guys, and then these are complex numbers, but you know everything else. So let me go to the punchline and free you from your troubles. So it's exactly this, right? This you should be able to find all these numbers at least once. Try to play with it, and if you have questions, you can ask me. But I must say that it's very non-trivial, and you will find wrong papers in the archive where they don't extract correctly the PMNS parameters, right? And this last question, actually, you heard about it today with Claudia. Someone asked, what happens? Do we always have two Mariner phases? And the answer is no, not necessarily, because if one of the masses is 0, one of the Mariner phases can be cancelled. Okay. If you want more details on this, I can explain to you, but I free you now from from this. It's already almost 5. Thank you, guys. Questions? Comments? Go.